In this lecture, we will talk about so-called mean field nuclear models. Now, of course, we know that the nucleon interaction is fairly complicated, and even the two-body problem of the deuteron requires all the techniques of computation to be used to uh, find out or to look at various observables and so on. The next three nucleon problem that is even more complicated, but approximate techniques have been developed by Faddeev and his collaborators. But if you go further from there, then of course things get even more complicated. If you were to start from the nuclear-nuclear interaction, indeed there have been groups which have done so-called ab initio uh, calculations, which involve Monte Carlo methods, and they have gone up to about A equal to 12 or 13. Okay, so of course we know that the heaviest nuclei, even the stable ones that occur in nature, uh, that is uranium-238. So there are 238 nucleons in that nucleus. So we are quite some distance away from hoping to calculate using ab initio methods, but nevertheless, these methods have been successfully used for the light nuclei. Similarly, there is another model that was quite popular in the 30s and so on, which is still being used in some specific cases, namely the cluster model. And this uses the modern cluster model actually uses something called the resonating group method. We will not get into that. This was just to state that there you have these ab initio models, you have the cluster model, and then of course the most popular model used for heavier nuclei is the so-called mean field model. And then you put in certain other effects which you see from experiments, namely the two particle correlations, quadrupole kind of correlations and so on, and those are put in by hand, and the parameters associated with these additions are actually varied to fit the data, and then of course you use them when you extrapolate it and get to either nuclei a little further off the stability line and so on. So the basis of these so-called mean field models is that when you have a nucleon in a nucleus, then it gets attracted by all the nucleons surrounding it. So there is an average attractive potential, and that's the so-called mean field. Okay. The short range of the potential, I mean, by what do you mean by short range? Of the order of a 1.5 Fermi or so, which is decided by the pion Compton wavelength, means that uh, the potential falls off pretty fast on the surface of the nucleus. So the nucleus surface is fairly well defined. Okay, so there is strong repulsion at the hardcore radius, which leads to a strong perturbation, and that can be termed as wounding of the single particle wave function when you have another nucleon close by. But this wave function heals at larger distances. Okay, so those distances within a distance less than the average nucleon-nucleon spacing, and this was shown by Victor Weisskopf in the 40s and 50s. Now, this is also the basis for why these mean field models work, because you have, of course, a very strong uh, repulsion at short distances, but uh, you don't see the effect of that at distances which are larger and which are sort of smaller than the nucleon-nucleon spacing in a normal nucleus. Then there is also the spin orbit interaction, which arises from the L dot S interaction in nucleon interaction. And of course, you can have this mean field, which can be spherical, but it can also be deformed. It can also be a rotating mean field. So these are the variations of the original spherical mean field model that was used to explain properties of deformed nuclei, to explain properties of nuclei which are rotating uh, fast, which means high angular momentum nuclei, and so on. So let's start with the simplest of them all, where you assume that nucleons are moving in a mean field but not interacting with each other. So they are moving in a constant potential with a sharp cutoff radius. So you put particles in a spherical box, and then you can compute the the phase density of these nucleons, and of course nucleons have spin half, so which means you can have a spin up, spin down, and you can actually compute the number of these nucleons. So this number, starting from this number density, which depends on the 4 pi p squared dp times the volume, where v is the volume of the spherical confining volume. Then this number comes out to be some factor times pf to the cube times the volume. And similarly, the neutron number is like this, with a Fermi cutoff momentum of pf of n, and the number of protons is given by this pf of p whole cubed times again a volume. Now, if you assume that these are confined to a sphere of radius r, then the volume is just given by 4 pi r0 squared a by 3. And if you assume that n is equal to z, as is so for lighter nuclei up to about let us say calcium 40, then n is equal to z is equal to a by 2. This is not too bad an approximation for heavier nuclei as well. This differs from the n is about let us say 0.6 of a, z is about 0.4 of a, not far from half of a. And then the Fermi momenta are equal to, you can equate them to a common Fermi momentum pf. Then this a by 2 comes out to be just something with some proportionally constant pf cubed into a, which means that now since r0 this a and a cancel out, so you get a relation between pf, the Fermi momentum of the nucleon, just in terms of this radius parameter. So for a r0 equal to 1.2 Fermi, you get kf equal to 1.25. So you equate pf to h cross kf, and then you get a kf which is 1.27, or a pf which is about 250, 1.27 Fermi inverse, or a Fermi momentum which is 250 MeV by c. Now, the Fermi energy can be also computed, just pf squared. This is non-relativistic, it's not the kinetic energy is much smaller than the mass. So, the Fermi energy is just about 33 MeV. Since the binding energy of the last nucleon is about 7 MeV, that means you require a depth, a potential well depth of about 40 MeV. This is somewhat shallower for protons, because of course we have not taken into account the Coulomb effect, and if you assume that this Coulomb repulsion leads to a small change in this potential of the order of z minus 1 times the r squared by r, then you can see that this potential well is a bit shallower for protons. If n not equal to z, then there is an asymmetry energy which arises, of course, as follows, that the kinetic energy term is just n times Tn for the neutron, and similarly for the protons, and then you can get a an energy which is contribution, which is T of A of z is equal to some constant times a to the 5/3 times something 1 plus 5 epsilon squared by 9, where epsilon is the asymmetry neutron to proton. So, if it is a small number like 0.1, then n by a is slightly larger than half, z by a is slightly less than half. Okay. So, this can tell you that since there is a, let's go back, there is a square dependence on this epsilon. Okay. So, if I go away from symmetry, I get an additional term which is proportional to n minus z squared. Okay. So, this is the full expression. T of A z is this, and this is the kinetic energy term. So, you can there is a first term contributes to the volume energy, this is just A times something. So, this is the volume energy term, and this is the isospin asymmetry term, and this actually gives a rationale for why we had this asymmetry term in the liquid drop model. If you remember some few lectures ago, there is a n minus z squared by A term, and this gives you a rationale for that term, because this is something here, which is proportional to epsilon squared. Uh, so we can see that this only contributes about half of that coefficient, and this is because this we have only considered the kinetic energy. The other half comes from the potential contribution, since V0 is deeper for this is deeper for protons in an enriched nucleus and vice versa. By the way, this kind of approach, the Fermi gas approach, can be also applied to white dwarfs to understand the broad features of white dwarfs and neutron stars. There is another fundamental quantity associated with the nucleus called the nuclear level density. This also can be extracted from the Fermi gas model. The background to this is as follows. As the excitation energy of the nucleus increases, the number of levels per unit energy interval, which is given by this rho as a function of excitation energy, this increases rapidly. So, initially you have discrete levels, then the density of these discrete levels starts increasing. So, they come closer and closer as you go up in excitation, and ultimately they start overlapping because the levels also acquire a width, and so there is a large number of levels, but they are overlapping in terms of their energy. So, this can be calculated for equally spaced levels near the Fermi energy. You can calculate the so-called single particle density G, and then you can see how many single particles can be excited. This turns out to be G of T, the single particle level density times the temperature, and that can be related to the excitation energy by the temperature. So, this Ex is just Gt squared. So, since this excitation energy can be distributed over 2n Ex single particle levels, it's a combinatorial problem, and you can see that this rho of x is proportional to exponential of 2n Ex times the log 2n Ex. Okay. So, this goes like exponential G of T or exponential square root of G times the excitation energy. So, this problem is actually analogous to find the number of finding the number of ways or partitioning an integer n using integers 1 to n. Okay. So, you have an integer n, so suppose I have an integer 5, I can partition it as 1, 4 or 2, 3 and so on. And if you have a large number, then of course there are a larger number of ways in which you can partition it, and Ramanujan Hardy in their 1918 paper, they found the number of ways you can partition it. It turns out that this is exponential some prefactor times square root of n. So, if you have equally spaced level, the problem can be mapped to just partitioning an integer, the number of partitions that you can get from an integer. And in fact, this kind of approach was adopted by Bethe in his paper. He in fact quotes this paper of Ramanujan and Hardy, and you can get a level density which is proportional to some 1 by E minus E rotational squared, but the leading dependence is coming from a prefactor here, exponential times the prefactor times the square root of E minus E rotational. Okay. So, the A parameter here is called, so level density parameter is approximately A by 8 for heavy nuclei. The E rot is just given by h cross squared by moment of inertia, where this moment of inertia is corresponding to the rigid body moment of inertia of a spherical nucleus, and this is the dependence of the rho E of Ex. Now, when a compound nucleus in compound nuclear decays, that means when you excite a nucleus to very high energies, it of course emits particles, because if that excitation energy exceeds the binding energy of the nucleon, then it can emit nucleons. It can emit a neutron, proton, depending on how high that excitation energy and whether it exceeds the separation energy of the neutron and proton. And so, this energy spectrum of course has a rise and a peak. The rise is for charged particles is because of the barrier, and of course even for particle like the proton, the neutron, for higher L's there is a so-called L into L plus 1 by R squared barrier. So, you have a rise and then you have a fall, okay, and the fall is of course dictated by the level density in the final nucleus. So, the rise is because you are now actually charged particles is easy to understand that there is a Coulomb barrier, and the higher you higher energy you go, it can more easily cross this Coulomb barrier. But at very high energies, then of course it again falls, and that is because of this transmission coefficient times the level density. Okay. So the particle evaporation spectrum is proportional to the final state level density as well as so-called transmission coefficient, which depends on L and EP. Of course, this is more complicated than that. The final spectrum is a summation over all of these, what are the allowed L's and so on. And it can come also from not just one step, but 2, 3 steps and so on. But the highest energy part of the spectrum, you just have to sum over the possible L's, because there is only one first step that can contribute. So something that sort was done in the measurements reported in this paper. So we looked at the high energy part of the spectrum, which is proportional only to the level density essentially of the final state, and this was done over a variety of energies so as to populate different excitations, and this was the total nuclear level density extracted after normalizing, of course, to some value here. So these spectra do not give you the absolute level density, but they do give you the excitation energy dependence, and this follows what you expect from, let's say, the Fermi gas model, broadly speaking. And of course, we have done this for the even nucleus in 70 germanium and odd even nucleus, and then you can look at finer measurements. So this is addressed in this paper. So you find that there is a difference between the level densities, especially at low energies, because there is something called nuclear pairing which takes place. Nucleons like to pair, and so when they pair, then the level density is slightly smaller than what you expect from the average behavior. So in principle, you can use this also to not just study pairing effects, but also shell effects, as we will see later. Okay, so now instead of just a flat potential, you can take other potentials which are more amenable in terms of their, their wave functions and so on, to calculate certain properties. And the easiest way to do that is to mimic the nuclear potential by a harmonic oscillator potential. This is one of the most used Hamiltonian, where you have the Hamiltonian given by the kinetic energy term P squared by 2m, and by the harmonic oscillator potential term, which is half m omega cross squared, omega 0 squared times r squared. Now, you can solve this Hamiltonian to get the eigenfunctions, and the quantum numbers in polar coordinates correspond to the radial quantum number nr, L the orbital angular momentum, m the projection of this L on the symmetry axis, let's say, or some axis that you choose, and then the projection of the spin on that axis. So, for instance, the energy spectrum shows eigenvalues, eigenvalue spectrum of E equal to capital N plus 3 halves, where L can change from n minus 2 to either 0 or 1, and the J can be L plus or minus half. So the degeneracy of each of these states is just 2 into 12 plus 1, and this is about n plus 3 half whole squared if n is much larger than 1. So now you can sum up all these states. So if you have states in this harmonic oscillator potential populated up to n, then you, for n prime equal to 1 to a maximum of n, you can sum this and you get a value which is n plus 2, approximately 1/3 of n plus 2 whole cubed. The number of radial nodes in a radial wave function is just this nr minus 1. So, as I said, you can mimic the real potential that a nucleon sees in a nucleus, which is to a very good approximation given by the so-called Woods-Saxon potential, where the potential goes like V0 divided by 1 plus exponential r minus small r minus capital R by A, where A is the so-called skin thickness of this potential, R is the half value of the density distribution or the potential distribution. And so, in this case, what is plotted here is for R equal to 5.8 Fermi, A equal to 65 Fermi, I think, if I can read it right, and the depth of the potential about 50 MeV, and the corresponding harmonic oscillator potential which mimics this. Okay. Of course, this is slightly deeper at small r and is shallower at an intermediate r, and then again is deeper at larger r and so on. But then, of course, it rises to infinity, which is of course not a realistic thing. But these harmonic oscillator potential, since most of the wave function resides here and not out so much outside, because of the Coulomb barrier for protons and also for neutrons. Anyway, the strong interaction is not felt at large distances and so on. At least for the bound states, this is not too bad an approximation, and indeed you can learn a lot of physics from studying this harmonic oscillator generated wave functions and so on. So, what is plotted here is, for instance, n equal to 4, L equal to 0 state. So, the radial wave function shows these oscillations, and it has 3 zeros if you discount the 0 at infinity. And for the n equal to 4, L equal to 4 state, of course, there is only the 0 at r equal to 0, but otherwise it shows a peaking at a slightly larger value of r, and that is because you have to, of course, account for this L equal to 4. And so, the difference is shown here between the harmonic oscillator potential radial wave function, which is this upper thing here, and it undershoots the so-called the Wood-Saxon form factor, the Wood-Saxon wave function, the radial wave function, which is computed numerically using this V of r for the Wood-Saxon form factor and put it in the Hamiltonian and solve. This is the radial wave function that you get. So, these are pretty close to each other. So, that is why this it makes sense to actually learn quite a few things from this mean field potential corresponding to that of a harmonic oscillator. Okay. So, the harmonic oscillator, of course, generates a very nice evenly spaced set of levels, and so for n equal to 0, n equal to 1, n equal to 2 and so on, you have the possible L values. So, the L value for n equal to 0 is just 0, n equal to 1 is just 1, but n equal to 2 is 0 and 2 and so on. Okay. So, the degeneracy is what is listed here, and this is the total number that you have if you fill levels up to a certain n. So, if you fill levels up to n equal to 3, then you get a total number of 40, up to 2 you get only 20 and so on. This is taken from the Bohren-Mortelson volume 1. The dimension of the orbit is given for a certain orbital NL defined by these two quantum numbers. Then this is given by just n plus 3/2 times h cross by m omega 0. And you can estimate the spacing between the major shells of harmonic oscillator levels by this relation. A times r squared is given by summation from n equal to 0 to n max of this quantity, and this turns out to be proportional to a to the 5/3 times r 0 squared. And similarly, you can also get another wave, I mean a is also equal to 2/3 of n max plus 2 whole squared, as whole cubed, sorry, and then you can relate these two and you can get a h cross. So, you can see that you have on this side something that depends on omega cross, omega 0, sorry, and something that is proportional to r 0 and a, or related to r 0 and a. And if you combine this from this relation, you can get a h cross omega 0, which is about 41.5 times a to the minus 1/3. So, the spacing between the harmonic oscillator levels goes down, but in a to the minus 1/3 way. So, for heavier nuclei, you have closer spaced single particle levels, and for lighter nuclei, you have them spaced out much more. That comes out if you just count these the states and so on. So, the closed shell magic numbers for a harmonic oscillator potential is this number that we had in the previous slide, So it is like 2, 8, 20, 40 and so on. So that is what is listed here, 70, 112, 168. But this is not what is observed experimentally. So up to here it's okay, but after that we observe differences in the so-called magic numbers. And so more realistic potentials actually lift the angular momentum L degeneracy which is there from this harmonic oscillator potential, and it lowers the energy of the high L states. However, still the magic numbers are, you don't get them right. And it was the contribution of Haxel, Jensen and Swiss, and independently Maria Mayer in 1949. These papers came close to each other in time, and they figured out that unless you add a spin orbit coupling term, you don't get these magic numbers that you observe right. And so the experimental data also says that the spin orbit partners j equal to L plus half and j equal to L minus half is such that the j equal to L plus half is lower than the j equal to L plus half n minus half, and this goes opposite to what you see in atomic levels. And in fact, this delta E LFS, which is the difference in energy between these two, is about minus 20 times the L dot S a to the minus 2/3. This is sort of proportional to the surface area of a nucleus, and it's pretty large. It's about 20 times this L dot S. So since the L max for a given n is proportional to a to the 1/3, so the spin orbit splitting is sizable compared to the spacing between these levels, between the major shells. So, for instance, if were you to put in this spin orbit coupling term of the magnitude that was mentioned there, then you can start out with let us say the harmonic oscillator potential, which gives you these states 1s, 1p, and then you can also put in the Wood-Saxon form potential, and then you get these states. And if you put in the L dot S interaction, then these states split. So the 1p state splits into 1p 3 half, 1p half, and if you tune this spin orbit coupling magnitude, then indeed you can get the right magic numbers. So you get magic numbers a equal to 2 or nz also separately equal to 2, 8, 20, 28, 50, 82, 126 and so on. So for instance, if the neutron number is this, any one of these numbers, then those nuclei are slightly more have slightly more binding energy than their neighbors. So these are the levels which are populated from, these are single particle levels which you get from the harmonic oscillator, the Wood-Saxon, and the Wood-Saxon plus spin orbit coupling. This is again taken from Bohr-Mortelson volume 1. So the key experimental observations which led to this deduction that if you have to get these magic numbers right, you have to put in a large L dot S coupling. So these observations came from neutron separation energies. I mean, these are 4 listed. There are a few more, and we will come to that in the next lecture. That the data comes from neutron separation energies as a function of Nz and A, the energy of the first 2 plus state, excited state, the A dependence of the elemental abundances in nature, and of course the nuclear level density as a function of A. So these are some of the evidences. There are more that we will discuss later, the alpha separation energies also and so on. Okay, so in summary, we have discussed the Fermi gas model to understand the origin of some of the bulk properties of the nucleus. The next step is to introduce a mean field in which nucleons move and its consequences in terms of shell structure. This is what we will do in the next lecture. Okay. Thank you.